You're listening to Worth Electronics' What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We'll be checking in with leading industry experts and Worth Electronic technical specialists. We're going to shine a light on interesting topics such as energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics' What's Up podcast. Electromagnetic interference, also known as EMI, has really become a serious problem because it can occur anywhere in electronic circuits, and it has unpredictable and sometimes detrimental effects. This issue has grown in recent years because of a number of factors, including increases in device frequency, high integration in electronic systems, higher power densities, and reductions in PCB thickness as well as size. The most common means of solving electromagnetic noise problems is to shield the system with conductive materials like shielded enclosures, foil tape, or conductive gaskets. Nevertheless, a large number of electronic devices have many parts that operate at higher frequencies that can cause complex EMI problems that cannot be removed with conductive shielding. So in order to avoid these issues, flexible absorber sheets, which are made of polymer filled with ferrite powder material, they can be used to suppress the unwanted high-frequency EM components. The different characterization techniques that we'll talk about today simulate specific problems focused on transmission lines, cavity resonance, and magnetic decoupling. These setups and experimental results will be shown in order to determine which material provides the best performance to reduce electromagnetic noise problems depending on the application. First, we'll discuss the properties of these absorber sheets. Now, one of the most important parameters that describes the material's ability to absorb direct and dissipated electromagnetic noise is represented by the part mu of the complex permeability. A material's permeability is the result of molecular composition and structure, and it's defined as the complex permeability. The real part quantifies the stored energy or inductive component, while the imaginary part quantifies the absorbed energy or the absorption component. The behavior of these parameters depends on the material composition, and it's frequency dependent. This means that it's very important to know in which frequency range noise levels exceed maximum permitted limits. So with this data, it's possible to establish a balance between reflection and magnetic losses depending on the application and the kind of electromagnetic noise. As permeability is frequency dependent, the correct material needs to be selected according to the frequency range where noise levels need to be suppressed. Standard specification doesn't generally give this information since they only state general parameters instead of absorption and reflection components. Nevertheless, it can be difficult to estimate the absorber material performance as it's a result of many different variables in addition to the absorber permeability. So some of these variables include sheet thickness, size, and geometry, as well as the distance between the noise source and absorber material. So this means that in basic systems, the attenuation of a certain electromagnetic noise suppression material can't be estimated. However, in order to study the effect in more complex electronic systems, it is often better to obtain real results through some experimental characterization techniques. It is more interesting to measure the absorbing capacity through experimental setups that make it possible to evaluate the material performance of several sheets that demonstrate different behavior. Thereby, several experimental tests are run that can be used to characterize absorber materials based on internal as well as external properties. The characterization techniques described simulated specific problems focused on transmission lines, cavity resonance, and magnetic decoupling. So these setups and experimental results will soon be explained in order to determine which material provides the best performance to reduce electromagnetic noise problems depending on your application. First up is the microstrip line method. Now, this technique makes it possible to evaluate the performance of the flexible absorber sheets in systems with transmission line issues through an experimental procedure. In this way, several sheets with different composition or thickness can be tested in order to obtain the maximum transmission attenuation power ratio in a specific application. These problems can appear in high-frequency data buses where digital signals switch in the frequency range of megahertz or gigahertz that can produce conducted noise on the data lines. An interesting solution in this sort of application is to place an absorber sheet on the data bus. This acts as a low-pass filter absorbing or attenuating high-frequency conducted noise. A method based on a microstrip line or MSL test is used to evaluate the attenuation of conducting current noise in a PCB or noise path when the noise suppression sheet is in place. Thereby, the MSL is employed as a transmission line, so a noise signal will be measured to know the sample absorption ability. This means this test simulates a noise source inside an electronic circuit and is therefore possible to determine the transmission absorption. Now, the manufactured MSL employed in this procedure consists of a PCB where the strip conductor is printed and two SMA-type connectors are connected in both ends. The MSL is composed of polytetrafluoroethylene, or PTFE, dielectric PCB material, and it has a length of 100 millimeters, a width of 50 millimeters, a thickness of 1.6 millimeters. A copper strip conductor with a length of 54.4 millimeters, a width of 4.4 millimeters, and a thickness of 0.018 millimeters. And finally, a copper ground plane located in the bottom. And this copper ground plane has a length also of 100 millimeters, a width of 50 millimeters, and a thickness of 0.018 millimeters. The SMA connectors are installed on the opposite side of the MSL, and they are connected with the end of the MSL through two vias. The absorbing ratio can be obtained by comparing the transmission line power ratio before and after installing the absorption sheet on the test fixture. In order to carry out the measurements, each end of a network analyzer coaxial cable is connected to each SMA test fixture ports. The network analyzer has to be configured to operate a signal source and signal receiver through measuring the S21 parameters to start the measurement procedure. You can see these results in Figure 1 of this podcast, and it shows all available materials in 0.3 millimeter thickness which have been measured. Next, we have the coaxial line method. Coaxial line experimental method provides a means of studying the noise suppression capabilities of the material to solve resonant cavity EMI issues. Cavity resonance is a problem, and it can appear when an electronic circuit is placed inside a metal enclosure. Noisy circuits usually cause the resonance inside the enclosure, which may cause interference problems or even generate a system malfunction. So considering this, after evaluating some absorber materials with several compositions and sheet thickness, it is possible to choose the sheet with the best performance to filter the resonant frequency. In this kind of application, a sheet is placed under the cover of the metal enclosure to absorb the electromagnetic noise. A means of reducing these issues is to place an absorber sheet inside the enclosure to attenuate or suppress the resonance by reducing the internal reflections. To evaluate this material in this kind of application, an experimental measurement system based on a coaxial line is used. So in this procedure, one terminal of the coaxial line is shorted with a metallic surface, and the reflected energy inside it is measured with a network analyzer. In order to characterize the absorption capacity of different compositions and or thicknesses, it's necessary to repeat this process, setting the absorber material attached over the reflector, and then compare the results. The evaluation of absorber materials in this experiment is carried out by measuring the reflection parameters, or S11, with the reference value set as the coaxial line without the absorber material. Next, the sample is placed between the reflection material and the reflective material before the measurement is made. By comparing reference and measured data, it is possible to study the performance of each sheet. The reflection attenuation measured with the experimental coaxial line method, as shown with 0.3 millimeter thickness, is in Figure 2 of this podcast. And finally, there's the magnetic decoupling method. Now, the magnetic decoupling is a common issue in electronic systems, which affects PCBs or devices with high-density layouts and their circuits. This electromagnetic interference situation is often observed when there is a noisy electronic component or circuit placed on a PCB that can affect nearby elements and components. An interesting solution which can reduce the unintentional coupling of this kind is to focus on filtering the electromagnetic interference by placing the absorber sheet on the noise source or protecting the interfered part. This technique analyzes the magnetic sheet's absorption capacity for reducing or suppressing the coupling by employing a microstrip line test fixture to generate the EMI interference and a near-field probe, or NFP, to measure them. This setup simulates a coupling system where one is used as a noise source and then the other is the receiver or the victim. The absorption effect is determined by connecting one port of the network analyzer to one terminal of the microstrip line and then terminating the other connector with a load of 50 ohms. Subsequently, a network analyzer is configured as the signal source and signal receiver, and the S21 parameters are compared before, this is the reference, and after placing each absorber sheet on the microstrip line. Then, the measured data with the absorber sample in place is subtracted from the reference. And once again, you can see the data we obtained through the magnetic decoupling technique in Figure 3 of this podcast. The graph shows the measurement of the WE-FAS with different materials in 0.3 millimeter thickness. Taking everything into consideration, WE-FAS flexible absorber sheets can solve a variety of EMI problems in different kinds of applications. Absorber materials have been characterized in order to be employed in applications with data buses affected by conducted problems, electronic circuits located inside an enclosure with malfunctions due to cavity resonance, and electromagnetic interference between components placed in the same circuit or in close proximity to it. Absorber sheets can provide us several advantages in controlling EMI, and this is confirmed with experimental techniques which provide results in terms of attenuation ratio depending on the kind of problem, therefore demonstrating the best option to use when solving a specific EMI problem. Furthermore, several thicknesses have been evaluated to demonstrate the performance of different products depending on the device space limits. Therefore, these materials can provide an innovative, straightforward solution without the need to modify or redesign the electronic circuit or the product. Attached images are available in most podcast streaming networks. To view all images, visit www.we-online.com/podcast. To download the complete application note discussed today, visit Worth Electronic online at www.we-online.com/appnotes. You're listening to Worth Electronics What's Up radio podcast, where each week we are seeing what's up in the world of electronics and PCB design. We're checking in with leading industry experts and Worth Electronic tech specialists. We're going to shine a light on our topics like energy harvesting, wireless power transfer, EMI issues, and so much more. Tune in to get technical design tips and applications during your commute, at your desk, or wherever you might be with Worth Electronics What's Up podcast.